Ionic bonding creates some of the most beautiful compounds. For example, these crystals of sodium chloride and fluoride. So we're going to learn about how these form. And basically, ionic bonds happen because atoms can transfer their electrons, those negatively charged particles on the outside of the atoms, can move around. For example, here is lithium with one electron on the outermost energy ring. We call that a valence electron. And it's leaving. That electron is moving away from the lithium and transferring over to the fluorine. And this is an example of transferring the electrons in the creation of an ionic bond. Here we can see lithium is a neutral atom at this point. It has 3 protons, 3 neutrons, and 3 electrons. The protons are positive, electrons are negative. They balance each other out to be a neutral overall charge. But this lithium atom is not stable because it has one valence electron in the outermost energy level of its electron shells, and it would be more stable if it removed that electron and just had the 2 electrons in the lower energy ring. As it loses that electron, it has a little bit of energy needed for that tiny bit. It's called the ionization energy. But then it becomes a positively charged ion. The reason it's a positive ion is because it has now only 2 electrons, which are negative, and it still has those 3 protons in the center. So with those 3 protons that are positive in the center and the 2 negative charges of the electron, it overall has a +1 charge. Now where does that electron go? Well, here's fluorine, a halogen atom, a type in the group called halogens, and it's sitting there innocently as a neutral atom, but it has 7 valence electrons. These electrons in the outermost energy level are called valence electrons, and having 7 of them, it would be much more stable if it actually had 8. So it's a perfect match here. This electron leaving the lithium can go over to the fluorine atom, and when it does that, it becomes an ion, a negatively charged ion, because it has one more negative charge than it has positive charges in the nucleus. So that becomes an ion, and the positive charge of the lithium ion is attracted to the negative charge of the fluoride ion, and so they become a ionic bond because opposite charges attract. And so the basis of the bond is the fact that opposite charges attract here. And it becomes lithium fluoride. So striving for stability, the atoms end up being charged. The only reason they're charged is because they're more stable with a complete set of valence electrons on the outside energy ring. Here lithium is stable with the 2 valence electrons now that it can have in that first energy level, and then fluorine is more stable with 8 valence electrons on the outside here. We see ions all around us. If we look up in space, there's ions in clouds of gas and dust that are illuminated by light from a nearby star. The atoms are energized, and then they lose some electrons, and then they glow, and these are transmission nebulas. We also see ions in lightning strikes. These plasma state of matter is ionized gases. So we do see ions physically with our eyes, and then the results of the bonding is quite beautiful, of course, with the crystals. And in order for these atoms to become ionized, it does require some energy to transfer, and ionization energy is just the energy needed to remove electrons. Metals have very few valence electrons, and so they can lose them easily with a little bit of energy added to them. Just a little energy is needed, not much. So they have a low ionization energy. And if we look at fluorine, by contrast, fluorine is a nonmetal, and it's very reactive as a halogen. The reason it's so reactive is because it has a very high electron affinity, and a very high ionization energy. It's not going to lose electrons, it's going to gain a few electrons in order to get 8 valence electrons. Because atoms are stable if they have 8 valence electrons in the outermost energy level here. So what happens when atoms gain or lose electrons? When atoms lose electrons, positive ions form. And it might seem strange losing something makes it positive, but remember that it's losing negative charges. So it's losing its negativity. Here, for example, magnesium has 12 protons and 12 electrons. That adds up to 0, neutral. If it loses 2 electrons, loses 2 of these negative charges, now it only has negative 10, but with a plus 12, it ends up having a plus 2 charge, and it's called a cation. I don't know why cation, it has nothing to do with cats, but we'd say magnesium becomes the magnesium ion, or cation. And when atoms gain electrons, negative ions form. And here, for example, sulfur has 16 protons and 16 electrons. If you add 2 more electrons, now it will have 18 electrons, which gives it a minus 2 charge. And we call negatively charged ions anions. And we often change the ending of a negatively charged atom. For example, sulfur, we change that ending to be called sulfide once it ionizes. So sulfur has a minus 2 charge as a sulfide anion. And there's a way that you can predict how much of a charge an ion will have, and it has to do with looking at the periodic table. If you notice group 1, they have all of them 1 valence electron. They would be more stable if they got rid of that 1 valence electron. They have a very low ionization energy. It's very easy for them to lose that 1 valence electron. In fact, if you've ever seen the really cool reaction of sodium with water, you're witnessing right there sodium giving away an electron to the oxygen, and it's dramatic and it releases a lot of heat. Basically, it explodes. So with 1 valence electron, they easily get rid of it and end up having a plus 1 charge as an ion. Group 2 elements have 2 valence electrons, and so they tend to lose those 2 to become stable, and so they have a plus 2 charge. Over here in group 16, for example, these elements have 6 valence electrons. The way I like to remember this is I go 1, 2, skip a few, 3, 4, 5, 6 valence electrons, and being with 6, they would be much more stable if they just had 2 more electrons and had the same electron structure as the noble gases. So they tend to gain 2 electrons, making them be negatively 2 charged. The halogens have 7 valence electrons, so you can guess they're going to add 1 more electron and become negative 1 charged. And the noble gases have 8 valence electrons, except for helium, but that makes them very stable. They do not react. So we can predict that the halogens over here with 7 valence electrons will end up being negative 1 charged. Everything in this group will have negative 2 charge when it ionizes, and everything in the first group will have plus 1, second group will have plus 2. It's helpful just to see those and know those particular groups on the periodic table. And what do ions have to do with bonding? What happens here? So we could say ionic bonds form when electrons are transferred from one atom to another atom. That's the basis, the basic fact. And ions of metals and nonmetals can combine by forming ionic bonds. Here we have sodium metal combining with chloride, a nonmetal, forming an ionic compound, which is neutral charged. Chemical bonds give materials their structure, and the structures formed from ionic compounds are crystal lattices. They're built of a repeating pattern of atoms. So you can see here in a sodium chloride crystal a very definite repeating pattern in this crystal lattice. Here's a better view of it. A crystal lattice is a regular, orderly arrangement of atoms, and they form from identical basic units to combine into one giant framework. And it can end up creating very beautiful crystal structures. For example, this one, and this one. And ionic bonds influence the properties of the compound. For example, when you physically hit them, they tend to break, and they break on special planes of fracture planes, cleavage planes. For example, this large green atom might represent a negatively charged particle. This might represent a positively charged particle. Notice the negative atom is surrounded by positive blue charges, so it's very strong. But and also the positive charges are surrounded by negative atoms. So again, there's very strong bonding there. But what if you took a hammer and physically forced very hard and rapidly, you hit this on the side? Now this little blue one is forced physically to the right, sideways, and it ends up next to the other blue one. The green one is forced sideways and is forced to be next to the other green. So suddenly all your positive charges line up next to each other and they repel. Your negative charges are forced physically next to each other and they repel. So as soon as you physically hit a crystal along the side, it's possible to force the like charges together, and then they instantly repel, and it causes the crystal to break along the plane between the two layers. So when you hammer them, they can be brittle. However, if you were to heat it up, they would be able to hold their shape for a very long time. Ionic solids tend to have very high melting points because, here's a positive charge, it's surrounded by all these negative charges, and a bit of heat energy, the shaking of the atoms, is not going to break that electrostatic bond. Minerals are really interesting because they break in special ways along their plane of weakness, and the larger visible shape of a mineral can actually represent an enlargement of their tiny structure, their tiny basic ionic compound structure. Here's some sample basic structures. There are 7 basic crystal structures for minerals, and they can end up combining in complex ways. Here's an aquamarine crystal structure. And here's a very large set of gypsum crystals. Note how large they are. This is a human being right here inside the crystal cave of the crystals in Mexico. And they're following the basic monoclinic structure of the ionic compound. This is marcasite, iron sulfide, following the basic crystal structure that's orthorhombic. If you look on the web at chemfiles.com/formulas, you can practice and learn for yourself how to write ionic compounds, formulas, the very simple ones. It's very easy if you just try it yourself. I think it's best to experiment on that website. Basically, you're going to try to match up your positive and your negative charges to be overall neutral charge. So ionic compounds need to be written as neutral. Number of charges of positives have to equal the negative charges. So here we have +2 from one calcium ion, and here we have -3 from one nitride ion. Those are not in balance. So if you think about the lowest common multiple between 2 and 3, what number do they both go into? That's the lowest. That would be 6. And so we can try and build up +6 as the total positive charges by adding 3 calcium atoms, and then -6 for the nitride with 2 nitrides. And notice now that the number of positive charges equals the number of negative charges, and it's all overall neutral. And we did that by adding subscripts here to represent the number of calcium atoms and the number of nitride ions. So this is overall neutral. You notice that we could have done the same thing by piling on 6 calciums and for nitrides. We'd have plus 12 minus 12, but that's not the lowest reduced formula. We should always write the formula in its lowest reduced form. So here's another example, simpler, cesium and telluride. Add one of each and you notice it's not balanced. We need more cesium, so now we have plus 2 and minus 2 of charges using cesium subscript 2 with telluride. So that's a nice little practice. You can try it on your own. I strongly encourage you to do that. So I hope that was helpful. Introduction to ionic compounds.